G'day, in this video we're going to be looking at applications of the Standard Model of Matter. In this video we're going to be revisiting a variety of dot points from lots of different parts of the course. And these are sections of the course which I didn't cover in complete detail because we did not yet have a complete understanding of the Standard Model of Matter. Today we're going to be looking at a variety of nuclear processes that involve the emission of particles which were introduced in the Standard Model of Matter. And we're going to be looking at how and why they form. We'll also start to unpack the idea that there are particle-antiparticle interactions, and that when particles and their antiparticle come into contact with each other, they actually annihilate and all of their mass is converted into energy. So our key learning intentions today, we're going to be looking at identifying common particles introduced in the Standard Model, introduce the idea of beta plus decay as an example of radioactive decay, look at how neutrino release is a necessity of both beta plus and beta minus decay. And because we're introducing new radiative particles, we're going to add them to our table of properties. We'll then have a look at particle-antiparticle annihilation and bring all of these concepts together to give a little bit more complexity to the proton-proton chain and CNO cycle that we looked at a few lessons ago. So let's do first a little bit of a revised table of some of our common particles, now introducing particles which belong to the Standard Model. You may see up and down quarks being referred to, and their notation is usually just a U or a D. But the ones that we're going to be focusing on a little bit more today are over this side. We have the beta plus particle, which we may also call an anti-electron, or we may call a positron. This is antimatter, and it's the antiparticle of the electron, meaning that it has the same mass as an electron, but has a positive charge. We would write this as 0, 1 beta. But there are many alternate expressions that we could also use. We could express it as 0, 1 E, beta plus, E plus, and for antiparticles as well, you may also see them expressed with a little bar on the top. So for example, 0, 1 E bar or E bar plus. We also have electron neutrinos and electron antineutrinos. Neutrinos are smaller than beta particles, so they also have a mass number of 0, but they're also chargeless. So we would usually write them as 0, 0 nu E. And nu is a Greek letter, looks quite similar to a V, but it is Greek letter nu. If we have the electron antineutrino, it's 0, 0 nu bar with a little E down the bottom. And you may also see them expressed without the mass number and the charge number. Muons are a particle that we've talked about as well in the past. While they're not massless, their atomic number is 0 because their mass is significantly smaller than, say, a proton or a neutron. They have a charge of -1 because they are a lepton. They're a second generation lepton, which is next to the electron. But you may also see an expression for a muon, which is just mu with a negative symbol without, again, the mass number or the charge number. So with knowledge of these particles, we can start to dig a little bit deeper with radioactivity and nuclear stability. In previous videos on nuclear reactions and radioactivity, we talked about the idea that you can have a nucleus with too many protons, and that if this occurs, there is too much overall Coulomb repulsion, and it begins to exceed all of the strong nuclear attraction between the particles, making the nucleus unstable. As a result, it's going to encourage a decay process. And if we look at our diagram on the right, we see that when there's too many protons, a lot of the time we see these orange boxes suggesting that there is beta plus decay that occurs. This is what's needed to remove positive charge from the protons and stabilize the nucleus. These beta plus particles are the positrons that we introduced in the previous video for the Standard Model of Matter. So what does that look like in practice? So for beta plus decay, we see that for a nucleus with too many protons, one of those protons will convert effectively into a neutron. This will keep and maintain the atomic number of the particle, but reduce the proton count. So where has this charge gone? Well, it's left through the emission of a positron, a beta plus particle, or an anti-electron, whatever you want to call it. This again occurs because there are too many protons, and the destabilization of the nucleus occurs because there is too much Coulomb repulsion. Because we're converting a proton into a neutron, we end up with the nucleus having a more stable neutron to proton ratio. What you'll notice though too is that in the beta plus reactions, as well as the beta minus reactions, I've added in not only the emission of a beta particle, but also the emission of a neutrino. In beta minus decay, there is always an emission of an electron antineutrino. So a particle and its antiparticle. And for beta plus decay, there is always an emission of an electron neutrino, an antiparticle, and its particle. So the general rule for beta decay is that if a particle is emitted, the antineutrino is released, and if an antiparticle is emitted, then the neutrino is released. So why does this happen? The first suggestion for a neutrino was actually made in 1930. There was some discrepancies in some of the more finer detailed experiments done with the early research of beta minus decay. When scientists measured the kinetic energy of the beta particles, they found that this energy was continuous from emission to emission, which didn't fit with the concept of the quantum model, which was starting to become more accepted and prevalent at the time. Pauli, who was a big supporter of the quantum model, suggested that this could be achieved if another particle was also being emitted with the electron in a pair, which at this stage was not being detected. But this particle would also hold kinetic energy. And so what he suggested was the total amount of energy that the electron and this unknown particle would possess would be quantized. But because it was shared between the two particles, this distribution of energy was not quantized, and therefore the particles could hold a continuous amount of kinetic energy, even though their total was quantized. Because it was undetectable, he suggested that the particle was probably neutral and was probably almost massless. This also meant that because there was no significant change in charge, mass, or any other property, it wouldn't muck up their understanding of nuclear reactions. Essentially, the particle was an energy carrier and nothing else. Turns out he was right, and the first neutrinos were discovered in 1956. And so not only does the release of a neutrino address some of the discrepancies and issues that was found with the energy of particles in beta decay, but as we developed our understanding of the Standard Model further, we found that this also helped to explain balances between a quantum property called the lepton number. And so for leptons, whether we're talking about electrons, electron neutrinos, muons, etc., they all have a lepton number of 1. And antileptons, such as positrons and positron neutrinos, have a number of -1. And protons and neutrons have a lepton number of 0. Therefore, if you were to undergo beta decay and eject an electron, this would change the lepton number of the matter that was left in the proton or the neutron. It would no longer have a lepton number of 0, it would have a lepton number of -1. This would therefore violate many principles of the Standard Model and our understanding of protons and neutrons and how they're composed. So in order for a lepton to be ejected and still maintain a lepton number of 0 on the proton or neutron, we would need to also release an antilepton, and this comes in the form of the antineutrino, which helps to explain why electrons and their antineutrino always are emitted in pairs. Conversely, if you were to go through beta plus decay and emit an antilepton, which has a lepton number of -1, in order to maintain balance in the lepton number of the proton, you would have to emit a lepton with the antiparticle. In this case, this would be the electron neutrino. So a positron with a lepton number of -1 and an electron neutrino with a lepton number of +1, if they're both emitted, means that there is no net change to the lepton number of the proton. Previously, we looked at different types of radiation from nuclear decay and summarized their properties in a table. However, we've just been talking about the idea that there are other particles that can be emitted as well: beta positive particles, electron neutrinos, and antineutrinos. So I wanted to add those to the table as well, and I thought we might just quickly review some of those properties now. So for beta plus particles, they are composed of one anti-electron, meaning that they have the same magnitude of charge as an electron, but the charge is positive. Their mass is also identical. Similarly to electrons, they would experience a large deflection from magnetic and electric fields when compared to an alpha particle because their mass to charge ratio is so much lower. But the direction that they would travel in the magnetic and electric fields would be the opposite to what we would see in a beta particle. Theoretically, beta particles have the same kind of ionizing ability as a beta particle does. The issue is, though, that beta plus particles will undergo annihilation when it collides with an electron. This is something that we're going to talk about a little bit later in this video. But when that happens, high ionizing gamma radiation is released. So even though theoretically it's moderate, we can also consider that the production of beta plus particles will lead to high amounts of ionizing radiation through the production of gamma particles. Similarly, the penetrating power should be the same as a beta particle, But if it comes into contact with a beta minus particle, another electron, it again will annihilate. Even though theoretically it has moderate penetrating power, it's probably going to annihilate quite quickly. Similar consequences again for the range in air. Theoretically it's a few meters, but it's going to be shorter than that because, again, it's going to annihilate. And its transmission velocity is very similar to a beta particle. For neutrinos and antineutrinos, these particles are chargeless, have a significantly smaller mass than beta particles. Because they have no charge, they don't deflect, and they're not able to ionize because they're so small. This also means that their penetrating power is extreme, to the point where it can pass through the middle of the Earth and out the other end. This effectively means that its range in air is essentially infinite. And finally, its transmission velocity is extremely close to the speed of light. So this brings us to particle-antiparticle annihilation. Essentially, when matter and antimatter interact, they annihilate. And what we mean by that is essentially all of their mass becomes energy. And that's transformed through Einstein's mass energy equivalence. So generally that means it's going to come out as gamma radiation. So as a quick practice, if we were to ask how much energy is released for the annihilation of an electron and a positron, that can be done by figuring out how much mass is annihilating and transforming and doing our conversion from there. This comes to be 1.64 times 10 to the negative 13 joules. However, in this particular scenario, there are 2 photons which are emitted. If we wanted to calculate the value of energy per photon, we could just divide this value by 2. And this gives us 8.19 times 10 to the negative 14 joules. So finally, let's revisit the proton-proton chain and the CNO cycle, both of which feature beta plus decay. So for both pathways, the first step includes the combination of 2 protons, which leads to beta decay to make deuterium. And so what we've learned today is that in beta decay, there's going to be an emission of a positron to remove that positive charge, as well as the emission of an electron neutrino. Further to that, we know that the positron is quite quickly going to come into contact with an electron. That's going to cause particle-antiparticle annihilation and the release of 2 gamma photons. What this means is we can write a summary of the proton-proton chain, which is a little bit more accurate, but certainly a bit more complex. If we were to add in the presence of 2 additional electrons, this leads to the emission of 2, 4, 5, 6 gamma photons, as well as 2 electron neutrinos. So in conclusion, we can say if we have 4 protons and 2 electrons, we're able to form 1 helium nucleus, 2 electron neutrinos, and 6 gamma photons. Similarly for the CNO cycle, there are 2 instances in the cycle of beta plus decay. These both lead to, again, the emission of a positron and an electron neutrino. Interactions with the positron and readily available electrons would lead to the formation of 2 gamma photons in both instances, totaling 4. Which means, again, we can write a slightly more complex overall reaction process for the CNO cycle. We still overall use 4 protons and need 2 electrons available to interact with the positrons. This still at the end forms a helium-4 nucleus, but through this process we've also formed 2 electron neutrinos, and in this case 7 gamma photons. Thank you very much, everyone. In the next video, thank you very much, everyone. We are approaching our final video. In this one, what we're going to be doing is bringing together a whole bunch of understanding around Einstein's E equals mc square, matter, nuclear reactions, standard model, stars, etc., to paint a picture of what happened during the Big Bang and beyond, and start to look at evidence for the expansion of the universe. But until then, have a good one.